Hi, I'm Kurt, and welcome back to Comp Sci 5. Today, we're going to have a whole heap of fun and learn all about heaps, otherwise known as priority queues. Now, we've already been through queues in the past, and we know that queues are a FIFO data structure, meaning the first in is the first out. A queue can be thought of like you're waiting in the line to get into a club, and you don't cut people in line because it's against the rules. However, what if some celebrity came in, some VIP? Well, surely they would be able to cut to the front of the line and get into the club because they have higher priority than you, and that is exactly what a heap tries to mimic in the computer science world. Structurally, you need to think of a heap as a full tree. For the purposes of this lecture, we're going to focus on a binary heap. So what a full means is that from top to bottom, left to right, you never miss a node. It's completely filled, so each level will be maxed out in terms of node capacity unless you're at the last level, in which case you may or may not have enough nodes to complete it. So behind the scenes, under the hood, if you will, of this heap machine is the array. The array is what is making this all happen and is what makes it all possible. We're going to get into that in a second, but the main rule, now this is the most important thing of the entire Comp Sci 5. You need to know for each node in the tree, the parent node has to have higher priority than the child node at all times. Now, priority can be dependent on what you are prioritizing in your program. Maybe you want low values, in which case it would be a mini heap. Maybe you want high values, in which case it would be a max heap. So here we have our full binary tree, and as you can see, for each node in the tree, the child node has less priority than the parent node, all the way across. Now, when you're making this in an array, we put the root node at 1 to make the math work in our properties of the array. So, as we know from arrays, they're indexed, which means we can grab an item on demand whenever we need it. This helps us because since it's a full binary tree, we know that by keeping track of that index, let's just call it k, 2 times that amount will be the left child of the node indexed at k. Therefore, 2k plus 1 would be the right child of that node indexed at k, and if you wanted to find the parent of a node indexed at k, you would take the node in question, divide it by 2, and take the floor of that, meaning rounding down. So if we look up here for the root node at 1, remember at 1 so that all the math works out nice and easy, 2 times 1 is 2. Therefore, at index 2, you'd expect to find the left child, and at 2, you see the element is 6, which is the left child of the root. Similarly, plus 1 would put it at 3, and yep, you guessed it, it's the right child of 1. Now, if we go through a parent of, let's see what the parent of 9 would be. 9 divided by 2 is 4.5, round down because that's what floors do, and there you are, you're at 4. So if you look at this array at index 4, you find the value is 7. So you would think that for 26, its parent should be 7, and that's it is. Magical. So now that we got those down, let's go through some common operations of a heap. Basically, you're going to either be inserting into a heap or you're going to be grabbing the element with highest priority. That's why you would use a heap in the first place, is to keep track of that priority. So for inserting, you're always going to insert the next element, the next node in the binary tree, the full binary tree, at the end of the array, naturally. At that point, you need to heapify, so you need to compare the node you just inserted with its parent node. If the child node has higher priority than the parent node, it violates the main rule that we went over, therefore you need to swap them. In doing so, you need to continue to do that comparisons until the child node has less priority than its parent node, then you know it's in its proper place. When you're removing the root node, you're grabbing the one of highest priority. To do that, you simply grab the node indexed at 1, and you grab it, you put it into whatever function you need it for to solve the problem you're trying to solve, and then you grab the node at the last element of the array, because you can grab it instantly. You grab it, you put it at the root at index 1, and now you need to heapify again and bubble down. To do so, you need to take the node you inserted, which is at the root, and you need to compare it with its children. If the children happen to have higher priority, then you need to swap with the child that has a higher priority of the 2 children, right? That's because you need to maintain this priority queue property. And you keep doing that until, when you're comparing with the children, if they have less priority than yourself, then you know you are in line with the rule of the heap. Super! Awesome! So now, we're going to go through an example.